Hello everyone and welcome. My name is Eva Dace and I'm a member of the marketing department here at Vitech Corporation. I will be your host during today's webinar as John Clark presents Stand on Standards. Before we get started, I'd like to review a few technical details. First, questions. Please feel free to submit your questions at any time via the question and chat function in the GoToWebinar window. We'll be monitoring these throughout today's event. We plan to respond to these at the end of the webinar, so please stay tuned. Second, recording. The webinar is being recorded today. If you are having technical difficulties during the presentation, an online archive with this presentation will be available within 24 hours of the live version. Now, let me introduce our presenter. John Clark is Chief Engineer at the Corporate Systems Engineering and the Corporate Systems Engineering Instructor at Northrop Grumman Corporation, with over 47 years experience applying systems engineering and software engineering. He is an internationally recognized subject matter expert in systems engineering and a founder and member of several NGC and INCOSE working groups. And now, the moment we have all been waiting for. Welcome, John. Thank you for joining us today.
Well, thank you, Eva. And this is John Clark, and thank you for attending today's Insight 2013 webinar. And thank you to Vitech for hosting this webinar and for inviting me to present it. And we'll go ahead and get started and take questions later, but let's go ahead. So this is Stand on Standards, and it's a title that I created and based on the system engineering process standards, and we'll give you an overview of those. And the point is that if you stand on those, you're on solid ground. Okay, so let's go ahead and proceed. So slide 2 is we've got some copyrighted information here with permission from the INCOSE handbook, from the EIA Tech of America organization, and thirdly from Vitech Corporation, some excerpts with permission there for their book on the primer for model-based system engineering. So let me get the keypad working here. Okay, so introduction to contents-wise, we'll talk about the objectives, purpose, expectation, and conduct of today's presentation, and the need for good system engineering, why we need it, some standards that we're going to talk about in this tutorial, this session, where they came from and where they're going in the future, and a little question and answer for you, a little exercise for you. What is a system? What is system engineering? What's the system engineering process in accordance with the standards? And what are these terms, iteration, recursion, and concurrency? What do they mean? And what is the system life cycle? Every system has one, and we want to describe that to you. So, and how do you manage a system engineering effort? And what is system engineering thinking? Some of my own comments there, thoughts about system thinking. Slide 4. We want to describe the system engineering funnels from a standards perspective, okay, including where they came from and what they say and what are their products and where are they going. There are many perspectives on system engineering, and the standards give a subject matter expert perspective that has stood the test of time for many, many years, as I'll show you, and I'm just trying to acquaint you with them and encourage you to use them. So we want to describe this relationship between system engineering and software engineering standards, and how systems and software engineering go together, and the attributes of the standards and how they're utilized, and talk about the system life cycle. And we do have a SE example and a hands-on exercise a little bit as part of another presentation, but we'll steer you toward that. I am the INCOSE system engineering instructor and the chair of the training working group, and as such I provide free webinars for INCOSE members and employees of corporate members of INCOSE. And if you send me a email at john.clark@incose.org or john.clark@ngc.com, Northrop Grumman Corporation, I'll tell you how to get access to those webinars and take advantage of them. So let's go ahead. And slide 5, we got the purpose here. We want to introduce you to the standards that you may be required to utilize in your work, and emphasize the processes for system engineering from the process standards perspective. Okay, and there's just a few of them. There are different views of the system engineering processes, and based on how the process standards present them, and by looking at multiple views, you get a comprehensive view, a more complete view, and we're going to present that to you today. And we're asking you to stand on the standards as opposed to relying solely on other sources such as listed here, the instructions, procedures, training programs you've taken, the courses you've taken, and even experience in performing some of the system engineering activities. So our expectation is that you'll have a good understanding of what a system is, what systems engineering is, and how to manage a system, what the processes are, and even software engineering from a standards perspective, and have a good understanding of those, including their heritage and where they came from and what do they say and what are the products of the system engineering effort and the relationships between the standards and where they're going in the future. Have a good understanding of the system life cycle and be able to apply the standards to a project and start small. Start the application on a small project and then grow from there. And we want to use a common terminology to enhance communications. Now the problem is that there is no common terminology in system engineering. Different standards have different terms, but we want to use the most common set of terms here today. And the overall goal is to learn the fundamentals of system engineering from a standards perspective. Slide 7, again, all ideas that you have and all questions you have might feel free to ask them and at the end. And what you say here stays here. We respect all beliefs and ideas. We want to encourage your participation, and hopefully your contributions and questions will enhance the learning experience for all of us. Class time is limited today to 50 minutes for the presentation, so brevity is a virtue. Like me, you ask an engineer what time it is, and they tell you how the watch works. The knob goes here, and the dial goes there, and the spring is here, and all you wanted to know was what time it was. So let's try to keep things brief. I'll try to do the same. Now, we don't want to discuss any specific U.S. Department of Defense projects due to the International Traffic in Arms Regulations, ITAR, but you can ask generic questions if you wish. We want to have the session be moderately comprehensive and stimulating, and hopefully your participation will ensure that it is. So slide 8, the need for good system engineering. There's 4 elements of balance. The human element, the interfaces, integration, and operability need, and the operational environment. Here we have the human element, or the balance, excuse me, and the mule up in front, and the load is too heavy for the horse or the mule engine. And then we have an interface, integration, and interoperability problem here where the 2 superstructures of the roadway somehow didn't quite come together. Okay, they weren't planned. Something went wrong. The human element here is an important element of the system, and you want to make sure that the human element is an integral part of the system, and the human performs functions that satisfies the requirements of the system. So take them into account and so forth. And then the operational environment, we want to consider the operational environment of our system, where it's located relative to other systems, and the environment and so forth, and not run into this kind of problem here that we show in the TV camera being behind the screen. So that's some of the need for good system engineering in a more humorous form. Slide 9, we'll get into the actual standards information. Now in this session, the scope and detail of the standards, there's different breadths of scope of the standards, from cradle to grave, from womb to tomb, from lust to dust, sometimes said. So different ones have different breadths of scope of the life cycle. And they have different depths of details. Okay, so then as far as how deep they go into the processes or the activities or the tasks or the subtasks or the outcomes and products and so forth. So different depths of detail. Now, the first standard, the EIA Electronic Industries Alliance Interim Standard IS 632, was published in 1994, and it was a successor to the unpublished MIL Standard 499B, which got killed by Secretary Perry, and we'll tell you more about that. It got caught up in standards reform, and so a lot of work had been done on it. And so the Electronic Industries Alliance saw its value, and they got together with IEEE and INCOSE and published this Interim Standard 632. And it's fairly, broad in scope and fairly good level of depth of detail. And then at the same time in 1994, the Institute of Electrical and Electronics Engineers, IEEE, decided that we needed a commercialized version of the standards for our constituents, and they took the EIA Interim Standard 632, which was a militarized version from MIL Standard 499, and basically translated into a commercialized version, And they went quite a bit deeper, down to the very low task and step level and so forth. And it is the deepest of all the system engineering standards today, even. And a very worthwhile document to read. Both of these are. So then in 1998, the Electronic Industries Alliance published the full-up 632, no longer an interim standard, but now the full-up 632, and it was broader in scope and deeper in depth. Again, but what they did was they went full commercial. They took out all the DoD, US DoD terms and technical reviews and baselines and things like that, and made it more commercial because their constituents are commercial, like IEEE. And then in 2003, 2002, 2003 timeframe, the International Standards Organization, International Electrotechnical Commission, published 15288, 15288, and that is the broadest of all the scope. It goes from cradle to grave. I mean, the womb to tomb. It's the whole shebang of the life cycle, but it's not very deep. Okay, it's very high level, to the process level and activity level. And it was meant for international commerce between nations where they could agree on something like system engineering. Okay, and now there are various guides written to it, and it's getting deeper as it evolves. It was revised in 2008, and that's the current version, and we're currently revising it now, and hopefully 2013, 2014 timeframe it'll be issued. We're also revising 632, and I'm a member of those two groups as well, and I was part of the 1220 revision. Okay, so let's go on to slide 10. Now, it's a little bit of history and kind of an eye chart, but the grandfather of all standards is MIL Standard 499 in 1969. Okay, and for software engineering, MIL Standard 1679 in 1968. And even at that time, we had these data item descriptions, the DIDs from the U.S. Defense Department, and these are basically templates for documents that they put in the contracts to say, well, produce this document and so forth under this contract. So those are basically templates. So the 499 evolved into 499A in 1974, and then in 1994, the 499B attempted to come out, but it was not released because Secretary Perry issued a letter saying we got too many MIL standards, and we've got standards for cookie cutters and toilet seats and hammers, and too much cost is involved in our contracts because of all these standards, so take them out and put in the contract only those system engineering efforts and documents and so forth that are really needed. Okay, so they what happened was the EIA interim standard 632 took 499B and issued it verbatim, and that's the last DoD style system engineering standard in existence that talks about the technical reviews and the baselines. And then in 1998 they revised it to be 100% commercial and so forth. But it's a good document. In 1994, IEEE again took 1220 and made it very commercialized, and that 1220 was revised in 1998 and again in 2005, and then it was fast-tracked to ISO IEC and became 26702 to the international community. Okay. Now back in 02, ISO IEC 15288 came out. Okay, and it was derived from all these other standards, and then it was revised in 2008 and so forth, and it's actually referenced in 1220 and so forth. So that's the evolution of the standards. Now there's some offshoots of that. The COSI SE handbook was based on these standards. The Defense Systems Management College Defense Acquisition University SE Fundamentals was also based on these standards. And the EIA Interim Standard 731, the System Engineering Capability Model, SECM, was based on these standards, and that became the CMMI, Capability Maturity Model for Integration. Okay, so now the software engineering standards, 1679 evolved into the A, the 2167, the A version, MIL Standard 498, and IEEE adopted that, and then they issued Joint Standard 016. Now, along with that, ISO IEC took and issued 12207, and they joined with IEEE, and it's a joint document, IEEE ISO IEC 12207 for software. Okay, and that's what's existing today. So on the far right, what you see is the 2008 versions 15288 and 12207 have been harmonized together. Okay, they can both be used simultaneously on a project, and they don't have any disharmony, let's say. Okay, and they're still being worked on even today. We've got some guides that came out, the technical reports 19760 and 24748 series of guides that came out to the 15288. Okay, and then at the bottom of the chart we have the data item descriptions, which I said were the templates and so forth for the deliverables, the documents, and for the put under contract to order a certain document, so forth. So real quick here, there's a legend down at the bottom of what supersedes what and what's based on if you want to go further, and even so, who references who. Okay, which documents reference which other documents, where they all came from, tracing back to their heritage. So that's a bit of an eye chart, but the point is that Mill Standard 499 is the grandfather of them all. Okay, and 1679 for software. All right, and they continue to evolve from mill standards to commercial standards to CMMs, and now they're going back to commercial standards. All right, let's go to the next slide, 11. So a little question for you, a little warm-up exercise. Answer the kinds of questions on your mind without looking at the materials ahead. You know, what is a system? We all have different definitions of what a system is. What is system engineering? What is the system engineering process? And things like that. So just be thinking of those, and we're going to define them in accordance with the standards, okay? And we welcome your definitions during the Q&A session if you'd like to amplify what you think a system and system engineering and your favorite definition of the system engineering process, okay? The slide 12, what is a system? Well, from Mill Standard 499B, which was published as the Interim 632 in 1994, we have this circle chart. This is kind of a context chart, and we have definitions here of what a system is from these standards. And a system is an integrated composite of people, products, and processes that provide a capability to satisfy a stated need or objective. Okay. Now there's some nice integrated composite. Well, it's integrated. And it's a composite of what? The 3 P's: people, products, and processes. Okay. Notice the people are listed first. Yeah. Hey, the persons, the people are part of the system. They're right in the definition. Products are part of the system. That's the hardware and software, and then the processes that build the system and that the operations of the system and the processes and services that it provides are part of the system. So those are the 3 P's. Provide a capability. Well, what's a capability? What's a high-level function, a high-level behavior to satisfy a stated need or objective of the user, usually the warfighter or whoever, the homemaker or whoever. Okay, so we look at this diagram and we see the system and we see the 3 P's: people, personnel, processes, services, and techniques. Okay, and products: hardware, software, facilities, data, materials. Those are some examples of those. And then the inner circle, we see the system engineering phases or stages of the life cycle here: development, manufacturing, verification, deployment, operation, support, training, and disposal. Okay, and then we see the primary system functions, the behaviors of the system. And then finally, at the center, the users, the customers, and the suppliers. Okay, those are part of the system also. Okay, the acquirers and the suppliers and the users are part of the system. So this whole context diagram indicates, you know, what a system is. Again, the 3 P's is probably my favorite definition. Now we can take this and say, well, let's expand it to the next chart here. Come on, chart. Can't get the chart to come up. There we go. You can put it into a triangle with the 3 P's, okay, kind of a nice little idea. Or you can put it into an org chart, like system, people, products, and processes, okay. It's kind of an organization chart. And you can list the these are subsystems, whatever elements, or whatever you want to call them, and you can list the subordinate elements under them, all right. So what is system engineering? Well, we've got my personal interpretation here. It's a translation from the problem space to the solution space. That's what system engineering does. It translates the problem into a solution or a set of solutions into the solution space. That's basically what system engineering does. And here in this solution space, we got the system of interest. That's the term that's used to talk about our system, that were currently under consideration. And then we have enabling systems to our system of interest, things that enable our system of interest to operate, like a fuel system or a ticketing system or navigation system to our aircraft. Okay. Then we have other systems in the operational environment, okay, that we interact with, that then the enabling systems interact with. Okay, so this is the getting into our solution space. So the definition here from 499 of system engineering is that it's an interdisciplinary approach, a multidisciplinary approach, okay, encompassing the entire technical effort to evolve and verify a what? An integrated and lifecycle balanced set of what? System, people, product, and process solutions. There's the 3 Ps again, the definition of a system that satisfies customer needs. That's the definition of system engineering from MIL Standard 499B and the Interim 632 that I like. Here at the bottom, I got a kind of a cute little quote. This is from the Boy Scout Merit Badge for Engineering. And it says, use the system engineering approach to make step-by-step plans for your next campout. You list alternative ideas for such items as program schedule, campsites, transportation, and cost. Tell why you made the choices you did and what improvements were made. That's requirement 5A of the Merit Badge for Engineering. That was kind of neat. Okay, well, slide 14. Now we're getting a little deeper. We've got what is the system engineering process? And what I've got here is a gold ring, okay, and within the center of the gold ring, I have the cornerstone classical system engineering process diagram. I mean, of all diagrams, this is the key diagram that started the whole thing, okay? And then outside the circle, I've got multiple views indicated by these arrows in these documents, multiple views of this classical process, the classical SE process in the center. And the idea of this chart is that multiple views give you a comprehensive view. The more views you look at of this center classical SE process, the better you'll understand it. Okay, and today we're going to look at the SE process standards view here in the upper left-hand corner that we talked about, all right? And the grandfather of them all is MIL Standard 499, all right? So now, it's basically input, process, and output, IPO, all right? The process input is different mission needs and scenarios and things that the user wants, whatever the problem is. Here's the requirements analysis, so we're going to look at the requirements for the system. We're going to look at the functional analysis and allocation. What's the behavior? What are the behavior of the system, okay, in terms of functions or use cases or whatever. And then we have the word synthesis, which is an older word for the word design. You take the information that you have and you synthesize it and produce the design. Okay, now here we have system analysis is performing trade studies and cost effectiveness analysis and things like that. And you're doing control, so you're doing configuration management here of what's going on and all these two-headed arrows. And we have a requirements loop that's feeding back from the functional analysis back into requirements. And then we have synthesis that's feeding back the design loop back into functional analysis and allocation. Then we have the verification loop that's feeding back from synthesis and says back to the requirements analysis, says yes, the design satisfies the system requirements. Okay, that's the idea there. Now, even though these are presented in the diagram as a stair step, like a staircase, implying that they're sequential, folks, forget that idea. They are not sequential. These are parallel, concurrent processes that go on simultaneously. Yes, you might not have heard that before, but the way it's implemented today is somebody writes the requirements, throws it over the wall, maybe somebody else later does a functional analysis, throws that over the wall, and somebody does the design, and then throws that over the wall to the user. Well, that's wrong, okay? That's a misconception, a misunderstanding of the SE process. The idea here is that these processes are simultaneous, and they go in layers or levels of the system, okay, and down from the from the external layer down to the lowest level of the system hierarchy, okay, in parallel, one layer at a time, okay? So these are sequential. And we have the process output, okay? So we're going to be looking at the SE process standards. Here's slide 15 is the cornerstone figure of all system engineering figures about system engineering. This is the one where it all started. And this is an amplification of the prior figure. Here we have MIL Standard 499B. And the process inputs, the processing in the center here, and you saw these requirements analysis, functional analysis, and synthesis before. and system analysis and control. And we have this output data down here, okay? So the inputs are the customer needs and objectives, the requirements from the mission operations, measures of effectiveness, environments and constraints, technology base, and what technology readiness levels are out there, prior output data. Prior output data is the prior time that this process was executed, it produced this output data on the lower right here. And the next time it's executed, this output data becomes input to the process, and that's what prior output data means. Okay, and that's iteration. So program decision requirements, requirements from standards and specifications. Let's look at the output. Integrated decision database. Well, what's that? Well, it's a database of all the decisions that were made, okay, and it's an integrated database. All the decisions were integrated together, such as the decision support data, the system, functional, and physical architectures. Yeah, all the specifications and baselines that come out of here are part of this decision database. Yeah, a specification is a decision. Okay, so balanced system solution is what we're looking for, the design. The design coming out of here. The balanced systems, the design is the solution to the user need. Okay, so we balance in terms of cost, technical, and schedule. Okay. So we have requirements analysis, analyze the missions and environments, identify the functional requirements, and define and refine the performance and design constraint requirements. Yeah, there's functional requirements, there are performance requirements, and there are design constraint requirements. They're all types of requirements. Okay, in fact, there's non-functional or the engineering specialty requirements, reliability, supportability, the ILLITs. Okay. Now we do the functional analysis, the behavioral analysis. Okay, we look at behavior diagrams and that sort of functional flow block diagrams. And we do some allocation. Allocation of what? Well, allocation of requirements to behaviors, to functions. Yeah, requirements get allocated to functions. Okay, and they're joined at the hip. So you define the top level functions and you decompose them to lower level functions, subfunctions. Allocate these requirements to the lower level functions. Okay, and the different types of requirements, and refine and define the functional interfaces between the functions, and then integrate the functional architecture. Then there's a requirements feedback loop here that goes on. That something happens in the behavioral analysis that affects the requirements. You got to go back and adjust the requirements. Then you go into the design, the synthesis, transform the architectures, the functional architecture to the physical architecture. Okay, the functional architecture comes out of the functional analysis. Now you want to get to the physical architecture. Define alternative product concepts. There's many types of concepts. Define the functional interfaces, internal and external, and define the alternative product process solutions. There are many. Now, the system analysis and control, there's not enough room inside the circle to put all the bullets. So they put them outside. Okay, you do trade-off studies to select preferred alternatives and do effectiveness analysis, risk management, configuration management, interface management, data management, performance-based project process measurements, such as in your system engineering management schedule, master schedule, technical performance measures, technical reviews, etc., different ways of doing it. So again, these two-headed arrows here indicate that system analysis and control is performing those functions in all of these areas. Okay, so that's the cornerstone of all system engineering. Now, I took in slide 16 and amplified it. This is the John Clark amplified version of the previous slide. What do they mean, requirements analysis? Well, define the requirements and interfaces, allocate the capabilities to the requirements, decompose and derive the requirements to sub-requirements, allocate sub-capabilities to the sub-requirements, define the requirements architecture, that's a term that I created, and develop the requirements traceability back from where the case came from, and establish the requirements baseline. Okay, so now these are numbered 1, 2, 3, 4, 5, 6, 7. Now down here at the bottom, I've got a note: do all the 1s, then all the 2s, etc. concurrently. Yeah, do the 1, define the requirements and interfaces, define the functions and functional interfaces, define the elements and element interfaces. Okay, then all the 2s, allocate capabilities to requirements, allocate requirements to functions, allocate functions to elements. Okay, and then decompose, then allocate those. Define the architectures and do some diagrams. You can read it for yourself. Okay, make sure, and this is functional analysis and allocation is what I call the inside out. Focus on the behavior of the system first, okay, and then define the requirements and design second, concurrently. A little different than what you're used to. Now, system analysis control. Now, the outputs here are these things: requirements architecture. By the way, on the right, I'm showing in these blue boxes. This is top group is the requirements architecture. The system R1, R11, R12. This is the father, the child, and the grandchild requirement. Okay, and the requirements tree. Then I show the functional architecture, the same idea, and there's one requirement mapped to one function. That's ideal. Okay. And then there's the element architecture, the physical architecture, where the one function is mapped to one element, ideally. So you got 1 to 1 to 1, and that's for this node here, okay? And that's how you do system engineering, all right? So let's move on, though. This slide 17 is the life cycle example. Now, this little egg chart, I call it, this is the little chart I showed you earlier, indicates application of the SE process as many times as appropriate during each phase or stage, okay? And we've got another note here of the technical review names, okay, the military style of technical review names from the MIL standard. So here during the market requirements phase, we do some needs analysis support. We apply the system engineering process. We look at technologies and opportunities, and we have some output. Well, that becomes the input to the next phase, and we during the concept definition and feasibility phase. These are the old DoD phase names in 1994, folks. So they changed names a lot. Alternative concepts, we look at alternative solutions, and we start writing a spec. See the dotted line? Okay, and we produce some output, and that's input to the next time it's supplied during the concept validation phase. We want to validate that our concept is valid and reduce risks, okay? And we continue work on our system specification. And in parallel with that, we're working on our functional baseline, the functional baseline right here, okay? So we get to a point here at the end here where this dotted line goes solid. Okay, well, what's going on? The functional line goes solid, and we're continuing to work on the allocated baseline. That's the element architecture. And we go through the alternative system review, the system requirements review, we get to the system functional review, and we baseline the system specification as the functional baseline. That's what you do in an SFR. Okay, now we continue to work here and do the development specs and start some product specs. And at the preliminary design review, we define an allocated baseline. It's really preliminary at this point. It's final at critical design review. And these different baselines in the system verification review is basically a functional configuration audit. And then you have a physical configuration audit. And you ask the question, does the as-built system meet the specifications? And does the as-built system match the documentation? If it does, you declare the product baseline and go into production. Okay? And I didn't mention the continuing SE processes, and finally end up with disposal. All right? Moving on to the specific standards, here's an abstraction of the 1220 document. You have requirements analysis, the inputs, and requirements validation. Make sure the requirements are valid. Yeah, you have to ask, are those requirements really valid requirements? Okay, and then you baseline those, and you have the functional analysis, the functional verification. Make sure that the functions satisfy the valid requirements. Then you have the synthesis or design, and you verify that the design satisfies the requirements, okay? Notice these two-headed arrows going up and down. And then over on the right here, you have the system analysis with trade studies and assessments going on simultaneously with the process on the left. And you have requirements, trade studies, functions, trade studies, and design trade studies going on with feedback going back to the analysis process on the left. And then finally at the bottom, you have the control, a configuration management control function that takes all the inputs, and then it's only through that the outputs occur. The process outputs come out of control, the configuration management process. Okay, that's 1220, all right? And it's more detailed than that, but this is an abstracted diagram. Okay, now the 19 is the EIA 632 diagram, where it's quite different. This is the full-up EIA 632 that was issued in 1998. And it was adapted in the Naval System Engineering Guide. It's in the NCOSI SE Handbook version 2A, and it's EIA 632, 1998. Well, you have the acquisition request coming in, you have some process in the middle, and you have the system products coming out on the right. Well, what's going on in the middle? It's kind of like an hourglass or a sandwich model. The top bread layer is the technical management with planning, assessment, and control. Okay, and the bottom layer, bottom piece of bread, is the technical evaluation, requirements and system requirements analysis process, requirements validation, system verification, and products validation. Okay, so those are the technical evaluation group. Now in the center here, we have acquisition and supply, system design, and product realization. Well, where's system engineering? Well, it's inside system design. Okay, requirements definition and solution definition. Okay, that's different names for those things. Well, where's functional analysis? Well, it got subordinated below requirements definition. Okay, so it got buried down in there. And along with object-oriented and structured IDEF0 and things like that are buried in there. All right, and DoD didn't like that system design term very well, so they went and issued their modifications to it, their Naval SE Guide. Anyway, it introduced the other concepts for engineering a system. The processes for engineering a system are acquisition, supply, and product realization, and management and evaluation. The system engineering processes are down in system design. Acquisition and supply is the supplier and acquirer. Two hats. You know, there's a supplier and an acquirer. And then realization is the implementation process. That's fabrication, coding, and training, and transition to use process. And then you have these up and down arrows, plans, directives, and status, and outcomes and feedbacks going up and down and up and down. It's a very iterative and recursive process, okay? That's 632. 15288 is this diagram here, slide 20, and I have both 15288 and 12207 for software shown here, and it's just a group of processes organized into these higher level groups. Okay, there are no process charts in this standard. You have to figure out yourself what processes apply when and how much. Yeah, here's the process definition. Now you figure out when they occur and how much they occur. That's your job, all right, and how they interact with each other. The point of 15288, as I believe, is all processes apply to all stages or phases simultaneously or concurrently. You have to figure out how much they apply. None of them are ever really zero. Okay, we have this green group, life cycle these are the organizational project enabling processes. These are the processes that enable projects to run. They're the organizational processes. They're not all the organizational processes. There are other things that the organization does, but these are the ones that enable projects to run. Okay, lifecycle model management, managing the lifecycle model and managing the processes. That comes out of here. Infrastructures, managing the resources like the facilities and test and computers and desks and things like that. Project portfolio management, you got it, folks. Portfolio. The organization looks at the set of projects as a set of stocks, as a set of portfolio. They manage the portfolio of their stocks, their projects, with this looking for a good return on investment. Okay, then if you're not giving them a good return, they'll cancel you or sell you. Human resources is people management. You know, attracting, retaining, training good people. Quality management is looking at the quality of the overall project from an organizational perspective. And the best measure of quality is a happy customer. Then you have agreement processes, the acquirer and the supplier. Okay, and an acquirer could be a supplier to a higher level acquirer. And a supplier could have subcontractors under them, and they could be an acquirer. So any organization can wear both hats, okay, at the same time. Then we have in the orange area the project processes, which are the project management group, project planning, and assessment and control. Plan the project, start it off, and assess it and control it. Make changes in the plan or change the project. Project support is decision management. That's doing trade studies mostly. Risk management, including opportunity management. Configuration management, managing the configuration items, the products that come out. Information management, it used to be the old library and called data management. Now it's called information management. And someday some people use the word knowledge management. And then measurement. Okay, this is measuring metrics, things like that. Now, the key system engineering processes are here in the purple. the technical ones, okay? And the stakeholder requirements definition process and requirements analysis. It used to be just all in requirements analysis, one process, but they separated out stakeholder requirements definition because of its high importance. And they want to emphasize the importance of that, okay? So they split it out. Then you define the requirements for the system, the shall statements, okay, and where they came from and how you're going to verify them. Then the architectural design of the system, okay, and this is the old word synthesis, but architectural design. Architecting is high-level design, and in this concept, design is lower-level design, okay? So it's just a matter of degree as to whether you're at high level or low level, and architectural design was coined as two words that covers both areas, both high level and low level design. Now in the future, these two will be split out into separate processes in the next version of 2015-288. Implementation is fabrication, coding, and training. Yeah, I said training because of the human element. And if something's going to be implemented in software, this is where architectural design says, you know, take these requirements and implement them in software. Okay, so here's the software processes over here where you've got the software implementation going on with requirements analysis, architectural design, and detailed design. Notice they put in the detailed design stage in software. Software construction, yeah, that's coding, okay, and integration and testing, qual testing. And the support processes, document management, quality assurance, verification, validation, reviews, and audits, problem resolution. They added some new things here, reuse processes for domain engineering, and reuse asset management, and reuse program management. Those are kind of neat things. Now, here we are at the bottom of the V with implementation. The V, you're probably familiar with the V. So we're going up the right side. Integration, verification, transition, validation, operations, maintenance, and disposal. Okay. Those are the technical process groups, all right? Integration is where you take and integrate the implemented elements together into a system. Verify, you want to verify that the elements and the integration of the elements satisfies the requirements. Transition is where you're getting ready to transition the system to the user. Validation is when you're mostly in the user site or a simulated user environment, and you're validating that the system meets the user need. And then you operate the system and then maintain it, keep it running, and then ultimately dispose of it, okay? So that's the 15-288 set of processes, and they're being expanded as we speak, all right? And this is the way the world is going. 15-288 is the world international standard for system engineering, and 12207 is the world's international standard for software engineering. And this is the direction the world is going in. And the other standards are trying to harmonize and keep up with this direction. And I'm involved in both of these. Okay, so 21 is, well, how are the books organized and how are the processes organized? Well, in 15-288 and 12.7, there's a set of processes. Okay, and each one has a purpose, and then they all have each process has a set of outcomes, and there are activities associated with each outcome, and each activity has a set of tasks. Okay, and then there's notes that apply to all the above. Okay, and in order to be normative or claim compliance with 15-288 or 12.7, you have to satisfy all the purposes and all the outcomes. All right, that's the structure of both. That's why they've been harmonized, so they can be both used together in the same project. All right, slide 22, one of my favorites, and I know the folks from Vitech will appreciate this. I certainly do. This is an excerpt from the Primer for Model-Based System Engineering, second edition by David Long and Zane Scott of Vitech Corporation, and it's one of the freely available books from Vitech, and in soft copy you can download it, and it's really a good book. And the first few chapters are in good old system engineering. The last chapter was on model-based system engineering, and in there they include this very nice figure, and I've added a few things to it myself. I've added the iteration, concurrency, and recursion. Now let me tell you about this chart. I think it's probably the best, most easily understood chart about system engineering process. So here you have level 1. Okay, that would be the external level to your system of interest. You have some external interfaces you have to satisfy, and that's level 1. All right. So here we have some source documents coming in, and we have requirements analysis, we have behavioral analysis, i.e. the functional analysis and object-oriented and use case analysis and those kinds of things. And then we have the architecture, the system physical architecture, and then we have the design verification and validation of the design. Now, I like these four wheels because when one turns, they all turn. Notice the cogs. When one wheel turns, they all turn. Okay, and that's concurrency, folks. That these processes are concurrent processes, simultaneous processes. Okay, and they are exercised again and again. They're iterated again and again. The same processes are applied at the same level of the system hierarchy, and that's called iteration. Okay, that's those two terms. Now, with this little fellow here is trying to build a model-based system engineering, and he's got this little globe and a little purple dot in the middle, and this is the model that they're trying to build of the system in model-based system engineering. And so then we go down and to the next level 2. This is be one level inside of your system, just inside the very top level of your system. Okay, trying to satisfy these external interfaces. So here we have, again, the same set: requirements, behavior, architecture, design. Now, if you, again, they're concurrently, they all turn, okay? And notice the model coming in is what came out of the top level, but the model going out is a little bit bigger, so things are getting more defined. More documents are available, okay? So if your project was terminated at this point, at this level, you could, these are documents, you could pick it up again. You've got all the answers at this level that you need. Okay, and you can pick it up again. And now we go down to level N, the lowest level of the system, however low that is, and you do the same stuff down there at that level. And if you finish that work, you're done, and you can put the project to bed. Okay, and then notice the sphere is a little bigger here. Now, if there's some reason to go back up, there's a little yellow arrow on the left. If you, for small reasons that you have to go back up, but hopefully there aren't very many of those. But the level of detail is increasing as you go down. I like this diagram. It really shows a lot. Now, recursion is going up and down the levels using the same processes again and again and again. That's recursion. Okay. Iteration is staying at the same level. Recursion is going up and down. And concurrency is everything going on in parallel. All right. Slide 23 here. What is the system life cycle? We've got the concept stage, the development stage, the production stage, utilization, support stage, and retirement stage. These are the stages in 15288. Forget the word phase. The word phase is not used in 15288, okay, as traditionally. Stage implies a degree of maturity of the system, not the time on the calendar, not the color of money, not anything else, just the degree of maturity of the system. Is it mature enough to go between the gates, to go from one stage to the other? Okay, that's the idea of stage. It gets away from the phase connotation. So you have a commercial integrator and commercial manufacturer. They have their different phase or stage names. Here's the U.S. Department of Defense with their, now they use the word phase, okay, still. User needs phase, material solution, pre-acquisition, their milestones, the system acquisition, sustainment, so forth. Here we have NASA's life cycle and Department of Energy. Now the bottom group here, typical decision gates, is kind of a summation of all the above: new initiative, concept, development, production, operational, and deactivation approval. So there's kind of an overview of all the life cycle stages of the system. Okay, and this is the way the world's going, 15288. All right, so how do you manage a system engineering effort? Well, there's a system engineering management plan. It's a plan to manage the engineering of the system, the whole system, all the engineering. You have a set of requirements, okay, a system spec. You have to break that down into work breakdown structure elements. Every element has a statement of work task associated with it. You take that statement of work task and define accomplishment criteria for that task when it's done, and you put that out on a kind of a calendar, not a calendar-based schedule, but an event schedule, and that's the system engineering master schedule, and it's now called the integrated master plan. There's a more modern name for it, but it's just a schedule of the events, and what are the accomplishments, and when do you know you're done. And then you have the detailed tasks down here. You put them on a calendar basis, a calendar schedule, and that's the system engineering detailed schedule, which in today's terms is the integrated master schedule, more modern term. Over here, we've got the example of preliminary design review and some criteria. Now, again, the SEDS is calendar driven. Okay, now also encourage using earned value management, earned value, which you take the difference between the budgeted cost of work scheduled and the budgeted cost of work performed, and that gives you a schedule variance. And the difference between that and the actual cost of work performed gives you a cost variance. Okay, so, and some TPMs and things like that. So those are kind of the key elements of a system engineering management plan on how to manage a system. So find some final thoughts. What is system thinking? This is my perspective. And my wife got me this t-shirt a while back, and here is a picture of what we think our Milky Way looks like. It's really not a picture of our Milky Way because we can't get a picture of our Milky Way because we can't get far enough away from it to get a picture. But what we do have is a picture of a nearby galaxy that we think looks like our Milky Way, and it's called the Whirlpool Galaxy. And we think we would be located about right here. Our solar system will be on this spiral of our Milky Way galaxy. And we look up at the stars at night and we look through the Milky Way, we see a white band of stars, of suns, like our solar system. That's what the Milky Way is, and we see it as a wide band of white stars at night, okay? And it's different in the northern hemisphere and the southern hemisphere, and whether it's winter or summer. You're looking inward or outward. But that's the idea, what I'm calling system thinking. This galaxy is a subsystem of a higher order system. What is it? Well, the universe, okay? And this universe has a system of systems. It has a number of galaxies in it, and there are interfaces between them, such as heat, light, gravity, microwave, infrared, all kinds of stuff going on between the galaxies. And within the galaxy, we have our solar system and the sun system, and we have planets within that, which are subsystems of the solar system. We have planet Earth, and within Earth we have the animal, plant, and animal and mineral systems, and within the animal systems we have humans, and humans are a subsystem of the Earth, and we all have subsystems in our bodies. Our bodies are a system of systems, and we have a respiratory, digestive, skeletal, muscular. We are a system of systems. How fearfully and wonderfully made we are. And then they have the organs and the cells and the molecules and the atoms and the parts of the atom, the gluons and different parts, now the God particle and all that stuff. It's all a system hierarchy, folks. It's all systems of systems of systems thinking, okay? And that's my view of system thinking, is looking at the universe around you and seeing it as a system of systems of systems and subsystems of a higher order system. And the question for you is, what is the universe a subsystem of? Okay. That's it. Summary 26, and we got some few minutes left for Q&A. This again, we've told you what we're going to tell you. We've told you, and now we're telling you what we told you, and hopefully we've opened your eyes and explained, exposed you a little bit to the system engineering standards and what they say and what their value is. Again, the key here is that multiple views give you a comprehensive view. Okay, we'll turn it back over to Eva. Eva, back over to you now.
All right, thank you, John. What a great presentation. So let's move on to the questions. We've already have some pretty great questions. Thank you for submitting those. I encourage all of those who haven't yet to join the discussion right now and submit your question via the question and chat feature in the GoToWebinar window. So our first question is from Stephanie. She wants to know if 15288 will be updated in the near future.
All right, great question. Yes, 15288 is being updated as we speak right now. I'm a member of the upgrade group, and we are trying to produce the next version, hopefully for release later this year or maybe early next year of 15288, and we'll be adding some processes up front. We'll add a business and mission process up front and ahead of stakeholders, and we're going to split architectural design into 2 separate processes, and maybe even include a appendix for the U.S. Department of Defense oriented system engineering process. Yeah, we're working on that as we speak.
All right, I have a question here from Edward. He asks, which standard do you recommend?
Good question, Edward. Thank you. Well, the the world's system engineering standard, the top tier standard is 15288. Okay, and I recommend that one for a good starting point and overall for where the future of system engineering is going. The other standards are more historical, legacy. They are ongoing and they are very, very good as well. The EIA 632 and the EIA Interim 632, which you can get as a Mill Standard 499B download. Just go to Google and get it. IEEE 1220 is excellent because it goes very, very deep, deeper than any of the other standards. It just depends on what you're looking for. I certainly recommend starting with 15288, and that's the basis for the INCOSE System Engineering Handbook. U.S. Department of Defense is adopting 15288 in their Defense Acquisition Guide, more so, and that's what the INCOSE certification is based on, is that handbook. So anyway, that's the way the world is going, and the other standards are trying to harmonize with it, and I'm a member of all those groups. Great question.
All right, and Charlie wants to know, will the INCOSE Systems Engineering Handbook be updated based on the 15288?
Okay, great question, Charlie. Yes, it will be. It's being updated now as we speak in parallel with the 15288 update and in parallel with the System Engineering Body of Knowledge produced by, now owned jointly by INCOSE, Stevens Institute, and the Naval Postgraduate School who developed it. But INCOSE and IEEE are taking it over as maintenance, and it's out there as version 1.0. So those three things are evolving, and yeah, the INCOSE System Engineering Handbook first draft has been drafted. It's being reviewed and revised now. We had hoped to have it issued next week at the International Symposium, but there's so much going on with 15288 and other things that we're going to need to delay its issue until late fall or maybe spring. And then it'll be called version 4.0, and when it is released, the exam will be upgraded 6 months later. You'll have 6 more months to use the old handbook for the exam until the new exam comes out based on 4.0, 6 months after its release. So yeah, there's quite a bit going on right there. And I'm one of the co-authors of the 4.0. A great question.
All right, a few more here for you. Ben asks, do you have any advice for systems engineering in rapid development programs or programs using agile software development?
Yes, great question. Thanks. Yeah, the Agile, I started the Agile community of practice in our company in Northrop, and I've taught seminars and webinars on it. And any advice to it? Yeah, train your people in Agile. Okay, make sure they understand it. Make sure your organization understands it. Train them and so forth. Make sure your customer understands it. Train your customer in Agile, okay, so that they see the value of it, because there's a lot of inertia out there of your teammates in your own organization, of your organizational leaders, and of your customers. There's a lot of inertia, and it's, what inertia is. It's the resistance of a body to change direction and motion. People are used to waterfall, okay, and they understand waterfall, and some of them are getting used to evolutionary or incremental, and they can understand that a little bit better. But Agile is so different that you need to make sure that the teams are all trained and your hierarchy is trained and they all become stakeholders and buy into the process, because it's a very, very effective process, mostly effective when requirements are highly volatile. If the requirements are highly changing and the customer or the user really doesn't know what they want until they see it, and they're going to be part of the team and be evolving with you as you go, Agile will work in a high requirements volatility situation. Okay, but if the requirements are all firm and well known and will never change, then the older methods, waterfall or incremental, will work for you. But again, just make sure everybody is trained in it and understands it before they maybe start small in an Agile project and then proceed to grow bigger and bigger, because it is extensible to even to systems of systems. Thank you.
Okay, Jose says, excellent webinar. What do you think of project control based on earned value, measured as requirements, implemented and tested? I read your company is using this approach.
Yeah, we use earned value, okay, and earned value is basically earned budget. You set up a budget for things that you intend to do, and as you actually do the work and complete work on those items, you give yourself credit for earning the budget associated with those items. Okay, so now you can ask yourself, well, what did I actually spend for those items? And then you can see a cost variance. And then you can ask yourself, well, how many items was I supposed to produce in this period of time? And you can see whether you're ahead or behind schedule in terms of budget. So that's basically earned value, and it's a very effective way of measuring progress and quality of your work. And what we want to make sure we do is include quality of the product in the giving credit for earned value. Not just the fact that the product is done, but that the product is of good quality to be granted credit for completing the work. So that's my thesis on earned value. It's very, very effective. Now, the other parts of the question I can't recall. It was a question about requirements and use of requirements and so forth design. Could you repeat the question, please?
Absolutely. He said, what do you think of project control based on earned value, measured as requirements, implemented and tested?
Yeah, yeah. It's very effective to measure the amount of requirements implemented and tested, verified, as giving yourself credit for earning the value budgeted for those requirements. Okay, for example, a set of requirements would have a certain value associated with implementing and verifying that those requirements were met. So it's a very effective way to measure requirements satisfied, and the earlier the better. The earlier and the lower the level of the requirements hierarchy that you can satisfy and prove that you satisfy and verify them, the better. Don't let them go to the last minute. Okay, hopefully I've answered the question.
I think you did. So Richard asks, what are the trends in integrating the different types of project and systems engineering tools? And by tools, he means applications such as core.
What are the trends in implementing various types of projects? Well, such as core. Well, core, if you listen to the webinar today, core core 9 has some new features, many new features, and one of the new features is the ability to do what's called product line engineering or reuse, where program or project artifacts can be shared across multiple projects, okay, in core, and reused in core very effectively. So that is a good trend toward product line reuse of assets as created in core. Now, I don't know enough about the other tools to know whether that feature exists in those tools or not, but I tend to doubt it. My knowledge of core is that it's the most comprehensive and the most complete tool. It's a full-featured tool that allows you to create a model of the system in the tool and exercise the model, both, verify that the requirements are met by the functions, exercise the functions, and they're allocated to elements, and do timing studies and optimize the allocations of requirements to functions and elements. That's the beauty of a exercisable tool like core. I'm not familiar with the other tools enough to know. I believe some of them do similar things, but the trend is that hopefully that more of the tools will interface with each other. ISO IEC has issued a standard, I think it's 10303, 10303, and there's substandards of that, parts of that standard. One of them is called AP233, which is a standard for interfacing between tools. Like a SysML-based tool and a DOORS-based tool would use this AP233 to have a standard interface between tools. And I noticed today that in the webinar today that Core now has a regular standard interface with DOORS as to import and export requirements with DOORS. And when a requirement changes in one tool, it ripples. It's linked to the requirement in the other tool, so they're both synchronized. And that's a wonderful feature. So those are just some ideas, things of where things are going with the tools. There's other vendors out there besides Vitek that are trying to integrate tools and so forth, and it's a real challenge to try to integrate tools together. But Vitek's Core is a tool of tools. It's all one tool in the same tool. There's no need to integrate anything with Core. It's a full-featured tool of its own internally, and then I can add the interface with DOORS for legacy DOORS databases and so forth. But it's that's my knowledge, and that's the trend, is to have a tool of tools that is model-based system engineering, and where the model of the system is in the tool, it's in the database of the tool, okay? And then furthermore, model-driven engineering is an extension of model-based, where in model-based the artifacts of the tools are used as guides for the future artifacts, but in model-driven, the artifacts of the tools are the future artifacts. One artifact is based wholly on the other and not as a guide. And I believe that that's the direction we're going in model-based, and we're with SysML diagrams and DODAP diagrams all available. So that's a big question, but that's my understanding of where the tools group is going. Now, in COSI, in their international symposium in Rome, Italy, that I attended last year, they have a tool vendor challenge. If you go to the COSI international site for Rome, you'll find a tool vendor challenge where 12 or 14 tool vendors were all given the same problem to solve and demonstrate their tool and outbrief them at a presentation track. And it's quite interesting to see that. And we'll do that again this year at Philadelphia. We'll have another track on the tool vendor challenge. Different problem to solve this time, but that's when COSI is trying to bring the tool vendors together and show the community the advantages of each one and their so forth. So that's basically what I know about tools. You asked me what time it is, and that's what how the watch works. Thank you.
All right, thank you, John. So we have some great questions coming in, and would it be okay with you if we do about 3 more?
Sure, you can do as many as you want. That's no
Okay.
problem at all. We keep going until the questions run out.
All right, great. So Jim wants to know if you are aware if DAU is intending to update the SE Fundamentals Handbook, or if it will be abandoned.
To my knowledge, no. It was issued in 2002 or 2003. It's not been revised since. There's no effort that I know of to revise it. Now, I could be wrong, but I haven't heard of any effort to revise it. What the DAU does is they work with the system engineering directorate in the Pentagon, and they support that, and together, along with some other agencies and contractors, produce the Defense Acquisition Guidebook, the DAG, and that is evolving almost weekly or monthly, and that is the DoD System Engineering Handbook. The Chapter 4 of the Defense Acquisition Guidebook is the Department of Defense's System Engineering Handbook, okay, and that's where they focus their effort in there, okay, and that is migrating toward 15288, Okay, and the 15280, if you look at the DAG and search for the word standards, do a word search, and you'll find ISO IEC IEEE 15288 as the top tier standard. Okay, and they do incorporate IEEE 1220 as ISO IEC IEEE 26702, which was the adoption of 1220 into ISO. So those are the only two standards that are listed in the DAG today in Chapter 4. So I don't think the Defense Acquisition University is going to be updating that 2002 SE process guide. It's a good guide. It's the DoD style of system engineering based on the MIL Standard 499. But I don't know of any effort to update it. Thank you.
All right. I have one from Brian here. He said, you mentioned that architecture design will be split in future releases of ISO and INCOSE standards. What are the new process areas?
What are the new process areas? Well, there's the architecture process and the design process. Okay, those are the names of the new processes. Architecture process is going to focus on the views and viewpoints of the architecture. And now they're not going to mention specific views that I know of. I mean, there's a functional view, there's a logical view, there's a physical view, and there are different views in the DoD architecture framework and Zockman framework, different specific names of views, the operational view, system view, technical view, and so forth. Those are not going to be listed in the body of 15288. They may be listed in an appendix to 15288. They're thinking of writing an appendix to 15288 for the Department of Defense use, in which they would write information about DODAF and things like that. But again, 15288 is going to split architectural design into architecture process and design process. Hopefully that answers your question.
I actually have one more question from Brian. He asked, how do you see the split between systems engineering and project management, or are they thought of as being integrated?
Good question. They're joined together. They are codependent. Okay, now the system engineer works for the program manager. Okay, the chief engineer works for the program manager. That's the hierarchy of who works for who. But the Gardner Institute has coined this term two in a box, where if you put the lead or chief engineer and the program manager in the same room, physical room, they will make the project successful by their communication. They will understand each other's roles and responsibilities much more effectively than if they were separated. Okay, they are codependent, one on the other. The system engineer is primarily responsible for technical effort. The program manager is primarily responsible for cost and schedule. Okay, but they are codependent. Cost, technical, and schedule are codependent on one another. So that's the distinction in the roles and responsibilities. The chief engineer is responsible for the entire technical effort from cradle to grave of the system. Now, it could be a different named person in the box. I'm just saying that the chief engineer is responsible for the entire technical effort from cradle to grave. The program manager is responsible for the entire cost and schedule from cradle to grave. But they're codependent on one another. That's, the system engineering chief lead engineer writes the system engineering management plan and owns the system engineering process, the engineering of the whole system, the entire system, all the engineering, not just system engineering, but all the engineering. And the program manager is responsible for managing the whole program, the overall program. And that's basically they both have risks. There's technical risks, there's cost risks and schedule risks, there's programmatic risks, and the risks are codependent, and they need to work together to make the successful system. Of the two people on a project, the two people that are most important to make the project successful are the lead or chief engineer and the program manager. And the idea is put them in a box, to put them together, two in a box, and they'll communicate. Great question, thanks.
All right, thank you, John. So that wraps up the Q&A for today. If we weren't able to answer your question today, we will contact you directly to ensure that your question has been answered. If you have any other questions or comments that you didn't send in today, we invite you to post those on the forum of our community site. You'll find that at community.vitechcorp.com. And as I mentioned before, a recording of today's webinar will be posted in the resources section of our website by the close of business tomorrow. Also, I hope you will join us for the rest of our webinar series, which continues for the rest of this week. Visit our website for details and registration. In closing, I'd like to once again thank our presenter today, and I'd especially like to thank all of you for joining us. At the conclusion of this webinar, a survey window will open on your screen, either in a new browser tab or in a new window. Please take a moment to provide us with feedback on today's presentation or on what topics you'd like to see covered in future webinars. Once again, thank you for joining us and have a great day.